In this lecture, we'll be discussing about the Ohm's law and the terms power and energy. So let us see Ohm's law. So Ohm's law is a fundamental law in case of electrical engineering. So it gives the basic relationship between voltage, current and resistance of a conductor. So it is a very important and fundamental law in electrical engineering. Ohm's law is stated as constant temperature, the current flowing through a conductor is directly proportional to the potential difference across its terminals at constant temperature. So this term is very important. Without this, Ohm's law is not correct. Ohm's law will hold good only if the temperature remains constant. So if we state the Ohm's law without this part, Ohm's law will be wrong. So I have noticed a common mistake made by students is that they'll omit this part and will state Ohm's law as the current flowing through a conductor is directly proportional to the potential difference across its terminals. But that is wrong. Ohm's law will be applicable only if the physical conditions remains as such. That is, the temperature should remain constant. So at constant temperature, the current flowing through a conductor is directly proportional to the potential difference across its terminals. So current is proportional to potential difference. So we can mathematically represent it as I, current, is proportional to the potential difference, that is the voltage. So mathematically I is proportional to V, and this proportionality can be replaced by a constant 1 divided by R, where R is the resistance of the conductor. So the equation becomes I is equal to V by R. So this is the equation obtained from Ohm's law, that is current I is equal to voltage divided by the resistance. I is equal to V by R. So this equation can be represented in two more forms. So from this equation we can write V is equal to I into R. So V is equal to IR, and R can be written as V divided by I. So all these three equations are very important. These are the basic equations relating voltage, current and resistance. Now, the Ohm's law is having certain limitations. We cannot apply Ohm's law under all the conditions, and also we cannot apply this law to all the materials, all the conducting materials. So let us see what are the limitations of Ohm's law. It is applicable to metallic conductors at constant temperature only. So we have already said this point. It is applicable to metallic conductors at constant temperature only. When temperature changes, the law doesn't hold good. So it is applicable to metallic conductors. That is also one point. It is applicable to metallic conductors and at constant temperature only. So the next point, the law doesn't hold good for certain non-metallic conductors. It is applicable to all metallic conductors, but it is not applicable to certain non-metallic conductors. An example is silicon carbide. For silicon carbide, the voltage current relationship is V is equal to K into I raised to M, where K and M are constants and M is a constant which is less than 1. And the next limitation is that for certain non-linear devices like Zener diodes, the law is not applicable. So the law is actually applicable to metallic conductors and at constant temperature. Then for certain non-metallic conductors, the law is not applicable. Example is silicon carbide. And also for certain non-linear devices like Zener diode, the law is not applicable. Non-linear devices means their voltage current relationship will be not linear. So these are the limitations of Ohm's law. So now let us see the term power. Power is defined as the rate of doing work. That is work done in unit time. That is the power. So mathematically we can represent power as work divided by time. If dW is the work done in a small interval of time dt, power can be represented as dW by dt, rate of doing work. So the unit can be joules per second because unit of work is joules and unit of time is second. So the unit can be joules per second. So now let us represent this equation in another way. So P is equal to dW by dt, and I am rearranging this equation as dW by dq into dq by dt. So there is no change. dq will get cancelled. So the same equation can be represented like this. So what is dW by dq? Work done per charge. Work done in moving a unit positive charge from infinity to a particular point. Work per charge, and we have defined it as the potential or voltage V. And what is dq by dt? Rate of flow of charge, and that is current I. So power, we'll get power as voltage into current. So power in an electric circuit is the product of voltage and current. So power is equal to V into I. And from Ohm's law, we know the equations for V and I. So let us substitute those equations to get different equations for power. So one equation is P is equal to V into I. Now substitute for I from Ohm's law. So from Ohm's law we know that I is equal to V by R. So substituting I is equal to V by R. Instead of I, let us substitute V by R. So equation becomes V square divided by R. This is another equation for power. Now substitute for V. From Ohm's law we have V is equal to I into R. So I into R into I becomes I square R. So these three are the equations for power. Voltage into current, V into I, V square by R, and I square into R. So these are very, very important equations. Next term is the energy. Energy is nothing but the capacity to do work, ability to do work. And mathematically, energy is expressed as power into time. Power into time. So we have the equation for power as V into I into time. So energy is VIT. Another equation for power is V square by R. So energy becomes V square by R into T. And another equation for power is the I square R. So I square R into time, I square RT. So these three equations can be employed for calculating the power. The energy.